from mechanical properties point of view, let's see how we have to estimate this properties. Okay. As we said, strength is one of them. Either you can test cylinder or cube. IS code recommends you to test a cube. Then we get your strength. Okay. And let's say that I get this stress strain curve behavior of concrete, right? So, and we know that, okay, here we have given that as FCK. FCK is your characteristic strength. We discussed in the first module also. We will define that again in the next slide. The point is the elastic modulus can be defined by multiple ways. Either you can take the initial tangent modulus, okay, or you can take secant modulus, or you can take, usually what we take is we take the modulus at about 45% of your compressive strength. Okay, if you take the 45% of the stress and then you draw a slope. Okay, so maybe I'll erase this. Okay, so that's why if you see here the blue curve, when you take initial tangent, it is going to be higher than that of your secant modulus that we are taking at about 45% of your compressive strength. So this slope of this curve is going to be lesser than your initial modulus. Okay, so the code defines your EC to be taken at about 45% of your compressive strength. And again, what is the ultimate strain that is specified by the code? For normal strength concrete, it is 0.0035. So we talked about epsilon CO, the failure strain or ultimate strain. That value, the recommended by code for design application is 0.0035. And peak strain, epsilon prime C, that we talked about. Okay, that is for concrete strength up to 55 megapascal. The code says that you can take it as 0.002. So if you go back to the previous slides, yeah. So if you see here, the peak strain increases, but it doesn't change much up to 55 megapascal. So that is why the code says, okay, you take epsilon prime C, a constant value of 0.00 for simplicity. Right. So we talked about this. This is the way we define your elastic modulus. So our code defines elastic modulus, which is a secant modulus at about 45% of your compressive strength. And these are your strain values that are used. Now, when you test a cylinder, even up to 40 megapascal concrete, different people have proposed some stress strain relationship. One of the classical one is proposed by Hognestad, which is also called as a parabolic model, because the relationship between stress and strain is actually a parabolic equation. Okay, so it is defined by this: Fc by F prime C is nothing but 2 times epsilon C by epsilon prime C minus epsilon C by epsilon prime C the whole square. Okay, and we know that F prime C is cylinder strength is going to be 80% of the cube strength, or cube strength is going to be 1.25 times your cylinder strength. You can convert. There is a conversion factor that is available for standard cube size and cylinder size. This Hognestad model can be used for concrete strength up to 40 megapascal. Now, to use this value, now what is that I need? At any strain epsilon C, I should be able to get Fc. Okay, that is what the intention of this equation is. If I know F prime C and epsilon prime C, then basically if I keep changing my epsilon C, then I can get my Fc, right? So epsilon prime C is, as I explained in the previous slide, it is usually taken as 0.002 for concrete strength up to 40 megapascal, right? And so once you test your cylinder or a cube, and then you can take your F prime C. So let's say I take a test cube and I'm getting a value of 40 megapascal. Okay. So what would be the cylinder strength? Cylinder strength will be 0.8 multiplied by 40, which is going to be 32 megapascal. So that is going to be my F prime C. So F prime C is given to me. Epsilon prime C is 0.002. Then I can nicely develop this relationship or parabolic stress strain curve model. This is a very simple model suggested by Hognestad, is valid up to 40 megapascal concrete. Now we have seen that as the strength is increasing, your peak strain is increasing, and your elastic modulus is increasing, and your ultimate strain is reducing. So people did a lot of research. One of the very popular model is the one that is developed by Thorenfeldt. It is valid for 40 to 100 megapascal concrete. So you can see here also the degradation in your strength is gradual in normal strength concrete. However, in high strength concrete, it is going to be very steep. So that also we need to account for it in our stress strain curve equations if you are using high strength. Why is it important? Though IS code doesn't give you the guidelines for at this current version IS 456 2000, it doesn't talk about how to accommodate, but it gives you freedom to develop your own stress strain curve if it is nicely calibrated from your test results. Okay, so this you can use it, a Thorenfeldt model. So how is this model is specified here is using this equation. Fc by f prime c is given by n into epsilon c by epsilon prime c times n minus 1 plus epsilon c by epsilon prime c times to the power of nk. Now again, f prime c you can get it by either testing cylinder or a cube, and epsilon prime c can be expressed as a function of your f prime c through some experimentally calibrated equation. Again, if I can know this n, k, epsilon prime c and f prime c for any value of epsilon c, again I can develop this curve, okay, which is what I want from design point of view. Now, how is this parameters epsilon prime c, n and k are derived? And we know that epsilon prime c is going to increase with increase in your concrete strength. And similarly, I need to find expressions for n and k. Now, let's see what is the significance of this n and k. Now, you see, n is a factor that accounts for curve fitting. So, that means what? The slope is going to change when your strength is, for example, initially it will all be elastic, and then the slope is going to change like this, right? So, the n is a parameter that accounts for how that slope is changing. Okay, so that is, in other words, it is basically the elastic modulus or the initial modulus divided by secant modulus, some form of secant modulus, EC by f prime c. It tells you how that secant stiffness is changing. That accounts for its curve fitting. And k is a factor that accounts for how fast the decay is. Okay, as we have seen that as you go higher and higher, the drop in strength is quite rapid, right? It happens very quickly. That's why the difference between epsilon c and epsilon prime c is keep reducing. So k is a factor that accounts for this post peak decay in strength. Okay, so people have done experiments using some server controlled, strain controlled testing, and they have proposed this equations for n, k, and epsilon prime c. So now let us see what is this. So for example, epsilon prime c, if I give you the cube strength, maybe I should say this is a cube strength. Okay, this is a cube strength. Then these are all calibrated as cube strength. So epsilon prime c is given as 0.8 FCU by EC times n by n minus 1. Similarly, n is also given, okay, as this as a function of your compressive strength. Okay, and you can write this as a cube strength because we deal with cube strength. So if you give it cube strength, the n value can be given. Similarly, EC can be defined, which is EC basically is the elastic modulus of concrete, and E prime C is nothing but your secant modulus of elasticity at peak strength. Right, so then k factor is given as 1 when in the ascending branch up to the strain reaches peak strain, k value is taken as 1, and for epsilon c values that are going higher than epsilon prime c, for which I'm calculating stress, k is actually taken as more than 1, and this is given by this empirical equation which is calibrated from your tested data, and again this is should cube strength. Okay, there is a difference between cube strength and characteristic strength. So we'll talk about characteristic strength in the coming slide. So this is a model which is widely used for getting the stress strain curve for concrete which are higher than 55 megapascal or 50 megapascal in strength. Okay. Now there is also going to be a effect of how fast you load the specimen. Okay. There is also something called strain rate effect. But for static test, usually our strain rates are 10 to the power of minus 4 per second. Okay, so I'm going to load this cylinder in a very slow fashion. Usually, I take about 2 to 3 minutes for testing. Okay, so you are ending up with a strain rate. So, what is the meaning of strain rate? How fast I am applying that strain, right? So if I apply fast, again your stress strain relationship is going to change. So we have done some experiment, and I'm going to show you just schematically how the stress strain curve is going to change if I keep changing my strain rate. And this is the one that we have set for about 30 megapascal concrete. You get this kind of nice curve. Okay. This is for static when the strain rate is less than 10 to the power of minus 4 minus 3 per second. It's a very, very small strain rate. And next one is for high strain rate of 30 per second. So 30, the strain value, see the concrete itself is reaching 0.005, 0.006 only, right? Now if you apply 30 as a strain rate in a 1 second, you can see how fast that rate of loading is. So you see here, the stiffness increases marginally. I am getting something very high increase in your strength, okay, which we need to account for it. For example, for a structural element that are subjected to high strain rate effect, the material property also is going to be enhanced. So that is what we are trying to see. When the strain rate is at 45 per second, again there is going to be increase in elastic modulus and also strength. And if it is at 60 again, you're going to get again some increase in your strength. So we increase using this dynamic increase factor, which can be expressed as a fraction of as a function of your strain rate of your loading. So using that, again I can modify the stress strain relationship that I have for concrete under static condition, which are tested under a very low speed of strain. Then using these factors, so as the strain rate is increasing, we are seeing that the strength is increasing quite a bit, and stiffness is also, or the elastic modulus is also increasing. Okay, so now we'll talk about so far we have discussed the failure mechanism of concrete in compression and how the stress strain curve is changing for normal strength and high strength concrete. And also we briefly talked about what is the effect of strain rate on the behavior of concrete. Now let us see what is the characteristic. I think briefly we discussed this in the first module. Anyway, we will look at it. So you have to choose. There is a variability in material property. There is a variability in load effect. So we have to reduce the material property or material strength values that we are using it in our calculations, and we have to amplify the load effects. That is what the limit state design approach is telling, right? So here we have to take characteristic strength, means you have to choose a strength value so that only 5% of the test results are expected to file. Now you can ask, why is it 5%? Is an acceptable value that is suggested by the code committee, so which is giving you good factor of safety. So that is why that 5% has been chosen, right? And similarly, for reinforcing steel also we have characteristic strength. So we'll talk about this again. We discussed this in the previous class as well. So if I design this mixed design, right, my minimum strength, this FCM is basically mean compressive strength. Okay, so characteristic strength is a value that if I choose, only 5% of this area should be less than the chosen value, right? So this is basically your Gaussian distribution, right? Normal distribution. So if the only 5% mean, it accounts for this as basically mean strength FCM will be basically FCK plus 1.65 times sigma, which is your standard deviation for this probability density, right? So if I want to design for a 30 megapascal concrete, okay, now what should be my target mean strength? It should be 30, should be characteristic strength plus 1.65 times sigma, and sigma for 30 megapascal for the code is given as 5. So which is basically 5. So this should be my FCM. So if I want 30 megapascal characteristic strength, I should be designing for at least 30 plus 1.65 times 5, which works out to be roughly 8.1 or so. So 38.1 or so is what the target mean strength that I should be designing for my mixed design, so that I get a characteristic strength of 30 megapascal. So similarly, the code gives you acceptable standard deviation that we can use. If you're designing for M15, you can take sigma as 3.5. If I'm taking M20 or M25, you can take 4. Anything from 30 to 60, we can take 5 megapascal as your standard deviation. So again, for if I want 60 as my characteristic strength, it should be mean strength should be 60 plus 1.65 multiplied by 5. So that's what it is. Right. So now let us look at how the curves. So first of all, you can ask me why is that code is taking, though I am taking, first of all, my mean strength is higher. I am knocking down by some factor to get my characteristic strength. That is what I have to use, right? So that's what we say. Okay, if you test this, this is what the code is proposing, right? This is an actual curve. Now again, what the code is saying is, okay, we are getting this FCK value by testing cubes, but cube is not the actual material property value. Actually, the cylinder represents the actual material property value. So code is saying that no, you multiply this by 0.8 to convert it into cylinder strength. That is one we are doing. And another factor that comes is there is also something called size effect. Okay, you are testing a small cylinders where you have good quality control, but actually your structural elements are quite larger in size. So and also when you do the casting process, there is something effect because of the density of the material. There is a tendency of the water to come up because of bleeding and other things. There is going to be lower strength that is possible in structural elements, right? So the code is saying that, okay, you convert this FCK, multiply by 0.8 to get your cylinder strength. Again, you multiply by a reduction factor of 0.85 to get your characteristic curve. First of all, this parabolic and remaining constant itself is not valid actually for strength anything more than 25-30 megapascal. Okay, but it gives us a reasonably good accuracy and good conservative estimation of your strength. So the code has kept it simple. Okay, it is actually not the way that we are going to get your stress strain curve when you test a cylinder. Okay, we have seen it in the previous slides. The shape is going to keep changing, and the curve is going to have a very steep drop when the strength is going higher and higher. But the code is suggesting this for as a simplified expression for our calculations. Okay, but if you cannot actually use this curve for in strict sense for more than 55 megapascal concrete as per IS 456. We have to validate it if you're using it for high strength concrete. But nevertheless, if you take this FCK as your value, the actual curve, again you knock it down by 0.8, which accounts for converting from cube to cylinder strength. And again, you knock it down by another factor 0.85 to get to account for that variations in the size effect, right? So ideally, you end up with 0.67 FCK. So that is why the characteristic curve, which is the black curve, all the stress and strain up to this peak, okay, it is knocked down by 0.8 and 0.85. When you multiply 0.8 and 0.85, you will end up with 0.67. So you get 0.67 FCK. In addition to that, in the last module, we talked about there is something called partial safety, material safety factor, gamma M, which is 1.5 for concrete. So 0.67 FCK, again it is divided by 1.5, then you get 0.447 FCK. So you can see, though I am using characteristic strength, but actually as per the design curve, I am using only 45% of your characteristic strength. Why is that? Because we do not want to have failure. Okay, concrete is most of the time use cast in place construction. There is going to be a lot of variability in your concrete strength. So that is why the code is saying that we are using only 45% of your characteristic strength in your calculations. So again, we go back to that Hognestad curve. So if I knock down this peak value FCK by 0.447, which is what it is. So this region, which is the region 1, okay, up to this, okay, where this equation is valid, which is basically from Hognestad curve. We saw that Fc is F prime C multiplied by epsilon C by epsilon prime C and so on. Here epsilon prime C is taken as 0.002 and we have seen that that is the range that usually materials will have for strength up to 40 megapascal. And epsilon is for any strain that you are calculating, doing the calculation, right? So this is the way we end up with 0.447 FCK in your design curve, right? From actual curve, you multiply it by zero point 0.8 and 0.85. Again, you divide it by 1.5 to end up with 0.447 FCK. And all the stress strain curve, entire regime is reduced by this factor. Okay. So, and then for strain greater than 0.002, we take a constant value of stress of 0.447 HCK. Again, that is also in strict sense, it is not correct, because if you test a cylinder, your shape will be different. But for simplification point of view, this is an acceptable design stress strain curve for at least for strength up to 40 to 50 megapascal. Okay. Now this is again influence of specimen size and compressive strength. And if you test cylinder, we are talking about the effect of aspect ratio. Okay, that means let's say I take a 150 diameter cylinder. Okay, but if I keep changing my height, height to the diameter, if I keep only 0.5, you can see that again, just like, in fact, if you go to 1, okay, right? So if you go to 1 means what? It is similar to cube, right? Diameter is equal, height is equal to diameter. It is basically going to like a cube with the same aspect ratio. So that's why if you look at for 1, you get a value of about 1.25 or so from the actual properties. Okay. So that is why for this, okay, you get about 1.25. That's why that 1.25 factor comes. But if you go to 2, you can see in the x-axis we are plotting height to diameter ratio. Okay, so if you see here, for a particular diameter, if I keep increasing this aspect ratio, you find that the relative strength, if I take this as 1, for lower values, I get higher values. If I go more than 2, it remains fairly, there is a reduction, but the reduction is not significant. Okay, that is why the code is saying that to avoid wastage of material, you test at least a cylinder of aspect ratio 2 to get your actual material properties. Okay, so this is the reason. So, but if you use cube, that's why the strength is amplified about 25%. So that's how you end up this factor. So this is why the relative. So 25% increase that it is going to give you. But in actual material property, you have to reduce it by 0.8, because 1 by 1.25 is nothing but 0.8. Right? So again, size effect also. Again, is this is valid for diameter of 150 mm, right? If I have, if I choose larger and larger diameter, then what happens? And we know that if the specimen size becomes larger and larger, there is a possibility of having more defects in the material. So the strength is going to come down. So that is why if you look at it here, so this, if you say 150 mm, then if you keep the strength value as 1, if you go for larger diameter, the strength is decreasing like this. And after a certain point of time, it plateaus. So the code is saying that if you look at this factor, okay, it's about 0.85. That is why that 0.85 size effect factor that is given there. That's why we multiply the FCK by 0.8 multiplied by 0.85, which works out to be 0.67 FCK. Okay. Okay, so this is with respect to the variation of properties for compressive strength. Now we know that concrete is strong in compression and weak in tension. Wherever tension is there, of course, we need to put the reinforcement to tackle the tension. And it is also important to understand for serviceability point of view and from crack width point of view, how the concrete is behaving in tension as well. So usually the tension strength of concrete is varying between 8 to 15% of your compressive strength. And tensile strength has a very important role in development, crack development. And the tensile strength varies as a square root of FCK. And tensile strength is usually simple, in a simple form. We can test it in bending and create tension and find out what is the bending tensile strength. And also another easy test to do is splitting tension test. And our IS code proposes modulus of rupture as 0.7 square root of FCK. Right? And the cylinder test, actually a split cylinder test, what we do is we put the cylinder in the transverse direction and we apply a line load, and then we create tension across the diameter we'll see that. Okay, so these are three ways. Either you can do direct tension, or you can do splitting tension, which is easy, and you can use modulus of rupture test, which is a bending test. Now, this is the tensile strength. Usually, it is adopted. We create this kind of a dog bone shaped specimen. Okay, and again, creating this geometry is also very important. Otherwise, it'll fail at the grips like this in a very sudden way. So, this doing tension test, direct tension test is actually very difficult, and you need to have a very stiff machine with a very good servo control system to really get the correct sustained curve behavior under tension. And also you modify the size like this as a dog bone shape to avoid stress concentration at the end, and you to localize the failure in the middle. So that is why we do this dog bone shaped tension test. Okay. And as I said, direct tension test to get the stress strain curve is actually a challenging task, and there is always a difficulty in testing and availability of sophisticated testing machine, right? And if I test this, you see here, if it's a plain concrete, and we know that as soon as the crack forms, there is nothing else, so your system is going to fail. So it reaches, and we know that in pure tension, it is from 8 to 10% of a compressive strength. Okay. Now, this is one of the tests that we did in our lab, and this is for ultra high performance concrete. We designed a concrete with a compressive strength of 150 megapascal, and it also had steel fibers, micro steel fibers, with a volume fraction of 2%. Okay, you see here, you get a nice pure tension strength of 8 to 9 megapascal. Depending upon how much fiber that you add, this values will change. And also, right after cracking, it is not going to fall suddenly, because the fibers are going to arrest the crack, and it is going to give you some lot of tensile strength in the post peak also, because now the fibers are transferring the load. Okay, so this is one of the tension tests that we did. I think this is what a close-up image of the test. You can see the fixtures have to be designed properly, and you find that also we use this digital image correlation technique to see the strain distribution, and you have multiple crack forming. Then finally one crack will start opening. When this one major crack kicks in, we call that as a localization strain, and so on. So in this way, you can get your actual direct tensile stress strain behavior, but it is slightly more involved and more difficult to do. Uh, Another simpler way to do is, as I've explained you, we can do this modulus of rupture test. Usually, what we do is we take a small concrete prism, and then we subject it to 4-point bending, and we know that when beam is subjected to 4-point bending, in this region you're going to have a constant bending going to be there, and whenever the bottommost fiber reaches its tensile strength, a crack will form, and because we're dealing with this the plain concrete, the crack will quickly propagate and it will lead to failure. So whatever that for the cracking load, we can calculate from your simple bending theory as Fr equal to m cracking by m. We are measuring the load. So from the load, I can calculate what is the bending moment. Then I can calculate your Fr, which is your modulus of rupture, right? So in this way, we can calculate. So we are interested in Fr. Moment will be given to you at what moment it is going to crack. Section properties are basically B and H of your rectangular concrete prism. So BH square by 6 is nothing but your section modulus. So 6 MCR by BH square will give you your modulus of rupture. So in this way, you can. Our code gives an expression of 0.7 square root of FCK. Another way to do a indirect tension test is basically splitting tension test. As you can see here, what we do is we put the cylinder in the transverse direction, and we apply a small line load, okay, and we keep pushing it. So why is it now developing in tension? You see, though I am applying compression, right? So my stress distribution here, if I look at it, if I plot it here, so right. So here it is going to be compression for a very small region, then it is going to convert it into tension, and then it is going to go like this. This is the stress distribution across this crack plane. Okay, so this is compression, this is tension. So almost about more than two-third or more than 80% of your cross section at this location will be subjected to tension. So this is again a very easy way of testing concrete to get its tensile strength. Okay. So splitting tension test, usually you get these values of about two-third of your modulus of rupture test. You will end up with lower value because in bending, you have only the extreme fiber that is subjected to maximum stress. Here, if you look at it, almost more than two-third of this cross section is subjected to more or less uniform tension. So you end up with lower values. And this is the way, this is a simplified formula that is given to estimate your splitting tension test. And usually it is about 0.5 square root of FMC. Okay. So this tension stiffening is a phenomena. Again, it's a very important phenomena. It accounts for, it is defined as the effect of concrete contributing in tension between the cracks on the stress of the reinforcement. So if you take a bare rebar, and if you, let's say this is a concrete prism and it is reinforced with one bar, and if I subject this prism to tension, what will happen is initially both with concrete and steel will start resisting this applied tension. Then you will have these kind of cracks that are forming along the length of the prism. Okay. Now, if I look at only at the cracked location, it has to satisfy the equilibrium. So the entire applied tension has to be resisted only by this rebar, right? As I apply more and more load, then you'll have more cracks that are forming. And what is tension stiffening is, though at the crack location only rebar is arresting this tension. However, if you move away from this crack location, at this location when you look at it, the concrete is also resisting that tension. So because of that, the stress in the rebar is going to reduce at this location. So this effect is called as tension stiffening effect. Okay. So as is at the crack, all the internal force will be carried only by the reinforcement. However, between these cracks, some amount of tensile force is transferred by means of bond because the rebar is connected with the concrete, and the rebar also usually will have something called this lugs, okay, or ribs that will help in transferring the forces. And there's also going to be chemical adhesion of cement paste with a bar that will help in bond. So it is going to be to surrounding. So it leads to reduction in reinforcement stresses and strains that causes the reinforcement strain at this uncracked location to be less than what you get at this cracked location. So if I plot this applied load, tension load on the y-axis and the strain on the reinforcement on the x-axis, we can look at a couple of scenarios. One prism with a very high reinforcement, lot of steel, and another with very low steel. So let us look at how this sustain curve. So if it is a fully cracked specimen, you can see that, of course, if I put low steel, it will have low loads it will be taking. Stiffness also will be less. And if I have a lot of steel, then the slope of this load strain curve is going to be higher. Now, because now more area of steel is there that is resisting this applied load. If you have concrete, again, if you look at this is a composite behavior. So if I put it, you end up with these two red color curves for the same prisms, one with high reinforcement ratio, another with low reinforcement ratio. This is blue color is only at the cracked location when I look at, only whatever that is taken by the rebar only. That is this, okay. Less rebar, less force, less load taken by that, and high rebar, high rebar. Now, when I look at it, as a composite system, this is the red color that I will get, okay. So that you can see that whatever that additional, for example, this low, this red and this blue has to be compared. This blue and this red has to be compared. So what you see here is you're going to get concrete is because the concrete is also contributing in tension. So initially both of them will take. Right after cracking, the contribution of concrete in tension is going to reduce and it is going to reach the level of what is taken by only steel. Similarly, for another prism with less steel also it happens. Initially, you're going to get a very stiff response because both concrete is not cracked. The entire concrete is until cracking. In fact, concrete is what it will take all the load. Only very less will be taken by steel. But then the contribution of concrete is again is going to keep reducing. Okay, so this is phenomena is called as tension stiffening. Now, depending upon how good the bond is, right? So this the increase in load resistance that is offered by concrete is what we call that as tension stiffening. Uh, so if you have a very poor bond, or if the bond between the steel and concrete prism is not good, then again the effectiveness of concrete in transferring the tension is going to be less. So you end up with slightly lesser curve than this red color curve. Okay, so this is called tension stiffening. Okay.